A character is a number that is constructed from a group element. So here is an abstract group element. And it depends on irreducible representation, which we'll label here by letter alpha. And its definition is very simple. If you have d alpha by d alpha matrix representation of action of the group, then we take its trace and we obtain that number. One obvious property of character is that if the group element is identity, then the trace of the identity is just the size of the d alpha by d alpha matrix. In other words, character or identity is dimension of the representation. What makes characters so precious to us is the character orthogonality relation. One way to obtain invariant information from a theory that has symmetries and expressed by group operation is to average over a group. So we take sum over all group elements and we divide it by their number. So if we average over 1, this would return 1. Character orthogonality relation is built from several bits. We take a character of one representation that depends on a group operation we average over, multiplied by any d alpha by d alpha matrix. Remember, character is defined in a d alpha by d alpha representation of the group. And we multiply this by another number, character. Alpha could be equal or different, but the group element appears here as an inverse. And that too can be multiplied by any matrix, which here we call F minus 1. And character orthogonality says that if we are looking at two different irreducible representations, so alpha and beta are different irreducible representations, then this sum should be 0. So that's captured by the canonical delta. Now, if they're the same, in some sense, we're taking some kind of sum of squares, and it turns out that this integral just becomes a character or a trace of the product of these two matrices. This is perhaps better understood by looking at two special cases. Suppose that these matrices H and F are just identity matrix. Then you can think of a character as a G-dimensional vector, where G is the dimension of the group. So it's labeled by group elements going from 1 to the dimension of the group element. So that's a vector, and it's multiplied by another G-dimensional vector. And together they form a basis in this G-dimensional vector space, an orthogonal basis. If alpha equals beta, then this is just square, but if alpha and beta differ, then they're orthogonal. And here is another variant of the character orthogonality relation. Let's say that H is some group element. H is the element of the group. Then if you multiply one of G's by H, but the other one is still just G inverse, then we relate sum over pair of characters to either 0 if representations are different, or if it's in the same representation, to character of this little element. This we'll find useful in what follows. So far we have discussed orthogonality of characters, and we thought of them as vectors in a space whose dimension is a dimension or order of the group. But there is also character completeness relation. says that if you take characters of two elements, G and H inverse, and we sum them over all irreducible representations, so over alpha. So now we think of this as a vector whose dimension is the number of irreducible representations. These two vectors are orthogonal unless G equals the inverse of H minus 1. So that's called character completeness. Why do we care? Because we'll be able occasionally to insert this chronicle delta on the right side. This is just identity. And this gives me a resolution of identity, saying that I can actually replace identity by the sum of irreducible representations. Let's illustrate this by the simplest imaginable example. Consider a dihedral group 1, D1, which consists of identity and reflection. So the way this acts, for example, it can act in any dimension, but in one dimension on a line, if you parameterize line by x, then reflection just replaces x by minus x. If I replace reflection twice, I'm back where I started. So in this case, the inverse of the operation is the group element itself. And if I act with this operator on a function of x, by definition, I obtain the value of the function at minus x. What are the characters of the dihedral group D1? It has only two elements, identity and reflection. So identity, reflection, and it happens to have two irreducible representations. The symmetric one, which is in crystallography conventionally called A1, and antisymmetric, which is in crystallography called A2. The character of identity is always 1, 1, because just a trace of one-dimensional representation. And the character of the identity element in antisymmetric representation is the same, but reflection gets a minus. Now that we have a character table, we can check the orthogonality conditions. So assume that we are looking at the second representation, A2, and both characters belong to that representation. Then the sum over the elements of the group, of which there are only two, is for the identity element, I get 1 from here and 1 from that, so I get 1 square. But for reflection element, because this is the second antisymmetric formation, I get minus 1 square. And that indeed is 1. So that verifies that the product of the same one gives me a Kronecker delta on the right-hand side. What if representations are different? So for example, this is character of symmetric and this is character of antisymmetric equations. The sum is still two elements. The first element gives me identity. I get a 1 in both representation. But when I look at the second element, then A1 still has 1, but A2, the antisymmetric one, has minus 2, and I get 0. So these two guys are orthonormal. How about the completeness relation? In that case, we take group elements. Here we'll take two different group elements, and we'll sum it over all irreducible representations. Dimensional group is 2, and the first irreducible representation, symmetric one, gives 1 to both identity and reflection. They have the same character. But when we look at the second antisymmetric representation, then identity gets 1, but reflection gets -1. And indeed, if the group elements differ, we get 0. So we have verified that at least for D1 this works.